Welcome to the deep dive. You're tuning in because you want to cut through the noise and really get a handle on complex topics. And today we're tackling something pretty fascinating, option pricing models.
Specifically, what happens after the classic Black-Scholes model everyone learns about first?
Exactly. We know you want to grasp that next level, the more sophisticated tools, but without getting totally bogged down in complex math.
Right, so for this deep dive, we're looking at a study, a really interesting one, that compares two different ways of pricing Google's stock options.
Yeah, it pits an updated, more complex version of Black-Scholes against a machine learning method, LSTM, it's called.
And our mission really is to break down how each one works,
Yeah.
look at their strengths, their weaknesses.
And figure out what it all means for understanding financial modeling today. By the end, you should have a much clearer picture.
Okay, so let's maybe start with the foundation. The original Black-Scholes model. It was revolutionary, wasn't it?
Absolutely. Black-Scholes, Merton, they gave us this theoretical price tag for options. It was a massive leap.
But it rested on some key assumptions.
Right, like constant volatility for the stock price and a fixed risk-free interest rate. Those were the big ones. It gave a starting point, a framework.
A vital framework, no doubt. But, well, real markets aren't quite that neat and tidy, are they?
Definitely not. Volatility jumps around all the time. Interest rates move.
And the original model sometimes struggled with those really sudden, sharp market moves, the things that create the volatility smile we often see.
So if the basic recipe doesn't quite match the real kitchen, you need to tweak it. That's the idea behind extending the model, right?
Precisely.
Yeah.
This study looks at making the model more realistic, specifically focusing on those two things, volatility and interest rates.
Making them not constant.
Exactly. Making them dynamic, or stochastic is the technical term, recognizing they change randomly over time, following their own kind of patterns.
Okay, so how do you even model something like changing volatility? That sounds complicated.
Well, the approach they used here is quite clever. For volatility, it's similar to something called the Heston model. Think of it like volatility itself follows a random process. It tends to revert to an average level, but it gets knocked around randomly.
So it has its own ups and downs modeled mathematically.
Exactly. They used a specific equation, d2 oxydia plus h2dia, to capture that mean reverting random behavior.
And they did something similar for interest rates too, because those definitely aren't fixed.
Yep, same idea. They used a model, kind of like the Vasicek model for interest rates. Again, it assumes rates drift towards a long-term average, but have their own random fluctuations.
So another equation for that, like DRABR, DT plus
So
SDWR.
that's the kind of thing, yes.
Yeah.
So now you have randomness in the stock price and in its volatility and in the interest rate. Much more complex.
Okay, so the original Black-Scholes had that famous formula. If you add all this complexity, how do you actually calculate the option price? Is there still a formula?
That's the catch. No simple formula anymore. When you add these stochastic elements, the math leads to what's called a partial differential equation, or PCE. It's much more involved.
A PDE. Okay, so how do you solve that?
You typically can't solve it perfectly with a formula. So researchers use numerical methods. In this study, they use something called the finite difference method.
Finite difference. Sounds technical. What's the basic idea?
Imagine breaking everything down into small steps. Small steps in time, small steps in the possible stock price, small steps in volatility levels, small steps in interest rates. You create a grid, like a spreadsheet grid.
Okay, a grid.
And instead of calculating smooth changes, you approximate the changes using the differences in the options value between adjacent points on this grid. You approximate those partial derivatives in the PDE.
So it's like estimating the slope between points on the grid instead of finding the exact curve.
That's a good way to think about it. It turns the complex PDE into a big system of interconnected algebraic equations, one for each point on your grid.
A big system.
Yeah.
How do you handle that?
Usually with linear algebra techniques, you can represent the system as a matrix equation. Then you use iterative methods like Gauss-Seidel or SOR, which basically make repeated calculations, refining the approximate option prices across the grid until the solution settles down and is accurate enough.
And you need some starting points, some rules.
Yes, boundary conditions.
Right.
Like, what's the option worth if the stock price hits 0? Or what happens way out at very high stock prices or as time runs out? These help anchor the solution on the grid.
Okay, I think I'm getting a feel for how this extended model works. So what did the study find when they used it on Google options?
They found some interesting things. Figure 1 in the paper shows how the predicted price changes with the strike price. And crucially, how that relationship looks different depending on the volatility and interest rate levels you assume.
Different how?
They saw this shift. The curve relating option price to strike price starts off, well, curve sublinear, but then tends to straighten out, become more linear, especially at higher strike prices.
Why would it do that, become more linear?
The thinking is that as the strike price gets really high, especially with these more realistic dynamics, the option's basic value, its intrinsic value, just stock price minus strike price, dominates. The extra time value and volatility value become less important way out there.
And figure 2 showed something too.
Yeah, figure 2 gives a nice 3D picture. It shows the price increasing as the stock price goes up and as you get closer to expiry, which makes intuitive sense. You can really visualize that surface.
How fast was this method? Did it take ages to calculate a price?
Actually, no. That was one of its strengths. The study reported a prediction time of just 0.87 seconds using this finite difference method. Pretty quick for this level of complexity.
Less than a second. That's impressive. And did it hold up well when they tested it against past market data?
They backtested it from May 2019 to May 2024, which included some pretty choppy periods, volatility spikes and all that. The study suggests it was reasonably robust across those different conditions.
Okay. Sounds promising, but nothing's perfect. What were the downsides? Where did this extended model fall short?
Two main things came up. First, it's still quite sensitive to the inputs. If your initial estimates for current volatility or the interest rate parameters aren't accurate, your calculated option price can be off. Garbage in, garbage out, basically.
Right. The inputs matter a lot. What else?
The other point is that even with stochastic volatility and rates, it fundamentally relies on certain assumptions about how prices move, often related to log normal distributions. Real markets sometimes have more extreme events, fatter tails, more skewness than those assumptions capture. So it might still underestimate the risk of really big market shocks.
Okay, that gives us a good picture of the extended Black-Scholes PDE approach. Let's switch lanes now. The other model they looked at was this LSTM machine learning territory. What is an LSTM network?
Right. LSTM stands for long short-term memory. It's a special kind of recurrent neural network, or RNN. RNNs are designed for sequential data, like time series.
And what's special about LSTMs compared to simpler RNNs?
Their main advantage is dealing with long-term dependencies. Basic RNNs can struggle to remember information from way back in a sequence. They suffer from the vanishing gradient problem. LSTMs have specific mechanisms to overcome that.
Mechanisms? Like what?
They have internal memory cells and gates. Think of the cell as holding information over time. The gates, typically a forget gate, an input gate, and an output gate, control the flow of information.
Gates controlling information. How?
Okay, so the forget gate decides what old information to throw away from the cell state. The input gate decides what new information to store in the cell state. And the output gate decides what part of the cell state to output.
Wow. Okay, so these gates are constantly learning what's important to keep, what to add, and what to use for the output at each step.
Exactly. They use mathematical functions based on the current input and the previous output to make these decisions. It allows the network to selectively remember or forget information over long sequences. There are equations for each gate, like FTT, CT, BI@T, that define these operations.
Got it. So how did the researchers actually use this LSTM for pricing Google options? What did they feed it?
They fed it historical data. Inputs included things like past stock prices for Google, historical volatility measures, and past interest rate data, likely sourced from places like Yahoo Finance or similar providers.
And how did they structure that input?
They used a windowing approach. So they might take, say, the last 30 days of price, volatility, and interest rate data as one input sequence.
To predict the option price for the next day.
Exactly. That sequence, that window, slides forward in time. The LSTM learns patterns within those windows. The model itself would have one or more LSTM layers to process these sequences, and then probably a standard dense layer at the end to output the final predicted option price.
In training, how does it learn?
Standard machine learning practice. They'd train it on a large data set of historical inputs and actual option prices. The model adjusts its internal connections, the weights, to minimize the difference between its predictions and the real prices. They probably use something like mean squared error as the measure of that difference, the loss function.
Okay, makes sense. So the big question, how well did this LSTM perform in the study?
Pretty well, actually, in terms of accuracy. Figure 3 in the study directly compares the LSTM's predictions to actual market prices for Google options in 2023 and 2024. Visually, the lines track quite closely.
And numerically, did they measure the error?
Yes. They reported a lower root mean squared error, or RMSE, for the LSTM. It was 15.23 compared to 20.47 for the extended PDE model. So based on that metric, the LSTM was more accurate in its predictions during the test period.
More accurate. But you mentioned a trade-off earlier.
Right. Accuracy came at a cost. The
Yeah.
prediction time for the LSTM was longer, 3.45 seconds, versus the PDE model's 0.87 seconds.
Okay, so slower to get a single price out.
Yes, and maybe more importantly, the initial training process for an LSTM like this takes a lot more computational power and time compared to solving the PDE. And if market conditions change, you need to retrain it, which again takes time and resources.
Makes sense. What other drawbacks did they mention for the LSTM?
Well, the big one is data dependency. These models need lots of good quality historical data to learn the patterns effectively. If you don't have that data, or if the market dynamics change significantly from the training period, performance can suffer.
And the computational cost, again, impacting scalability.
Exactly. Training and retraining are resource intensive, which could be a practical hurdle if you need to price thousands of options in near real time.
Okay, so we've dug into both the extended PDE model and the LSTM network. Let's try and pull this together. What are the main takeaways when comparing them?
Well, the clearest comparison is that accuracy versus speed trade-off we talked about.
Yeah.
The LSTM in this study offered higher accuracy.
Lower RMSE.
Right. But it was slower for individual predictions and much heavier computationally, especially for training. The extended Black-Scholes, using the PDE approach, was faster but less accurate according to their results.
So it's not like one is just flat out better.
No, not at all. I think a key insight is that enhancing traditional models like Black-Scholes, by adding those stochastic elements, does create more realistic and powerful tools than the original. It's a valuable approach.
And the machine learning side.
It clearly shows the potential of techniques like LSTM to find complex patterns in market data that maybe the formula-based models miss, leading to potentially higher predictive accuracy. But you pay for it in computational cost and data needs.
So they both bring something useful to the table.
Absolutely.
Yeah.
The study really concludes that these approaches can be seen as complementary. Understanding both gives you a more rounded view of the challenges and possibilities in option pricing and risk management.
Right. So just to sum up then, we started with the basic Black-Scholes, saw its limitations in the real world.
Then we looked at extending it, making volatility and rates dynamic, which led to complex PDEs solved numerically more realistic, computationally efficient.
And then we explored the LSTM approach, data-driven, potentially more accurate at prediction, but needing lots of data and computing power.
Exactly. It's a journey from simpler formulas to complex numerical methods to sophisticated machine learning. Each step reflects an effort to better capture how markets really behave.
So here's a final thought to leave you with as you process all this. Think about how that balance model, complexity, data hunger, computational speed, maybe even interpretability might push different users towards different models. A high-frequency trading firm might have very different needs and resources compared to a long-term institutional investor or a regulator. What factors beyond just pure accuracy or speed might be critical in deciding which tool is right for the job in different real-world scenarios? Gives you something to chew on.
A lot to think about indeed.
And that's what we aim for here on The Deep Dive. Thanks for joining us.